So hi guys, we are back with another video that is we are going to discuss the paper 11, right? So this is the 2019 past paper. So under the 2019 past paper, we are going to discuss the questions related with the units and dimensions and the mechanics lesson, oscillation, waves, and then I have forgotten to mention optics as well, and then heat also, right? So there's 1, 2, 3, 4, 5, 6 lessons, 6 sections involving, right? So actually from the 2019 paper, the questions from all these 6 lessons have been included, right? So all the questions out of these 6 lessons have been shortlisted and then included in the paper. So we are gonna discuss these things in detail, right? So yeah, if you have not yet covered the paper, first of all try the paper alone once, and then thereafter you can go through the discussion, right? Okay, so let us discuss the 2019 paper, that is the paper 11. The first question, right? So what they're saying is, which of the following is not a fundamental unit? Is not, right? Which of the following is not a fundamental unit? So when you talk about fundamental units, what are the fundamental physical quantities that you have? So first is length. You have length, right? Fundamental physical quantities, the unit of it is meters. And then what do you have? Mass. You have mass. The unit of it is kilograms. And then you have time. Unit of it is t, right? So and then you have current, right? The unit of it is amperes. And then you have what? Temperature, right? The unit of it is Kelvin, right? So not degree Celsius. You need to be very careful that the unit of the SI unit of temperature is Kelvin, right? And then thereafter substance, right? The amount of substances that is measured in moles, right? So and then light intensity is there, light intensity, right? So actually it is measured in candelas, right? So how many physical quantities are there? 1, 2, 3, 4, 5, 6, 7. So these are the all fundamental physical quantities, and these are the fundamental units, right? So mass, kilogram, time, mass, kilogram. Sorry, this is not T, right? Sorry, this should be what? Seconds, right? So mass, kilogram, seconds, amperes, Kelvin, moles, and candela, right? So these are the physical quantities, which means, so mass is there, okay, candela is there, Kelvin is there, mole is there, which means the non-fundamental unit is what? The joules, right? So the answer is going to be joules. All right. So next, let us see the second problem. So in the second problem, they're saying the dimensions of the gravitational constant G. They're asking the dimensions of the gravitational constant G. So to solve this, right? So we need to know the equation for the gravitational force, right? So we need to know the equation for the gravitational force. That is, what is it? F is equal to G mass m1 m2 r squared, right? So if there's two objects of mass m1 and then of another mass m2, then the gravitational force, that gravitational force Fg between them is going to be what? It's going to be the product between the mass and if the distance between them is r, so the gravitational force is directly proportional to the product between their masses and the square of the distance between them. So if you remove the proportionality sign, it's going to be a constant. That constant is mg, right? So that is the gravitational constant. We need to find the dimensions of this gravitational constant. Let us subject it. So Fg r squared m1 into m2, right? So in that case, G is equal to, what is Fg? Actually the if we need to find the gravitational, if we need to find the dimensions of the gravitational constant, then we need to get the dimensional constant dimensions of all the terms in the right. Okay, so it's like this. So what is the dimension of the force? Actually, the dimensions of forces are mlt minus 2. This is a well-known thing. What is the dimension of r? R is the distance between them. The distance is written in what? Length, right? So length, and it's squared, L squared. So mass is m. The dimension of mass is m. Once again, the mass dimension is m. So m to m, 1 m cancels. L is L cube. L cube. M, this m comes up. M minus 1, T minus 2, right? L cube, m minus 1, T minus 2. M cube, m cube, L cube, m minus 1, T minus 2. This is the answer, right? So let us move on to the next problem. So let's go for the next question. That is, this question is going to be based on thermal physics, guys, right? So yeah, so this is also going to be based on thermal physics, the thermometry part, right? So let's see what it is, right? So there's a lot of concepts that we need to absorb out of this question. So you need to be patient in order to completely get something out of this question, right? So yeah, so let us see which of the following statements is incorrect, right? So which is incorrect regarding thermometry. That is what they're asking. So if you see the first one, they're saying there must be a measurable physical quantity that varies with temperature. So obviously, you know, if there is a thermometer, right? If there is a thermometer, definitely there should be a there should be a measurable substance, right? So there should be a substance that the thermometric substance should actually vary with temperature, right? If this doesn't vary with temperature, if this substance doesn't vary with temperature, then what are we going to measure, right? So definitely that is true, because like whatever the thermometric substance that we use inside thermometers, it should vary with time, vary with temperature. That is why we call it as a thermometric property, right? So actually the main thing that a thermometric property should contain is, it should, first of all, it should vary with temperature. And then there are a few other concepts as well, like it should it's better if it varies linearly with temperature and all. So there's plenty of stuff that in order that we need to consider as well. So but this is correct, it should be a measurable physical quantity that varies with temperature, right? Okay, next, of course, the mercury glass thermometer consists of a thin wall. So it consists of a thin wall, they're saying. Does it contain a thin wall? Obviously it contains a thin wall, right? So why does it contain a thin wall? So actually it is true, right? So you need to understand it consists of a thin wall, that is true. So let us see why it should have a thin wall. What is the reason for the thermometer to contain a thin wall? So actually the main reason for it is for the main reason for the thermometer to have a thin wall is, right, that is for higher response, like quick response, right? So that the reason is going to be quick response, right? So quick response, how do we get a quick response out of a quick response? So the thing is, if you consider the wall, right? So if the wall is somewhat thin, then from the substance, right, so quickly heat can transfer into the mercury, right? Into the mercury from the outer liquid, that liquid or the fluid or whatever it is that we need to find the temperature of, heat can quickly transfer into the mercury. So what happens if it is too thick? If it is thick, what happens is, the heat needs to conduct through this thick solid part, right? It takes some time. It would take some time. If it takes some time, it would take a longer time to show a response, right? So if heat is completely absorbed by the mercury column, then only it will start to rise. Then only it will start to rise. So if this is quite thick, then what happens is, it will take a longer time for the mercury to heat up and then to show a response. So therefore, quick response, in order to have a quick response, of course, the presence of a thin wall is very important, right? So one thing is, when you cover these past papers and all, do not only target to get the answer, right? So actually these are once again not going to be given in the same way, but they're going to change the questions and give you, right? So in that case, you need to understand the concepts behind these things, right? So because like if they change these kind of questions and give you, so it should be like you should have already analyzed these things in detail. So okay, let us see the third solution. So by using a mercury glass thermometer with a very large mercury bulb, with a large mercury bulb, the range of measurements can be increased. Okay, so what they're saying is, okay, if you use a small mercury bulb and then if you increase the size of the mercury bulb, can you change the range of the temperature measurement? Can you change the range of the temperature measurement? No, that cannot be done, right? Because by changing the size of the bulb, you can't change the range. Actually, the range depends only on the substance, right? It depends only on the substance. So because like if you consider mercury, right? Mercury's melting point is something around, as I remember, minus 38 degrees Celsius. So mercury's boiling point is something around 356 degrees Celsius. So the range is this. This is the range. This is the maximum range that you can measure. So the like you can go up to minus 38 degrees Celsius and you can go up to 356 degrees Celsius. This is the range that you can go up to, right? So therefore, like by changing the size of the glass bulb, you can't change this range. If you need to change the range, you need to change the substance straight away. The thermometric substance, you need to change it, right? So you need to understand that is the incorrect answer. Right? This is the incorrect answer. So therefore, this is the solution. This is the solution. But like actually our target is not to get the solution, right? So you need to understand, if you are only targeting to get the solution of the past papers, then of course that is not how you need to analyze questions. You need to analyze the other answers as well, right? So let us see the fourth solution. They're saying two different types of thermometers may have slightly different readings at the same temperature, as all the thermometric properties are not equally sensitive. Exactly, that's exactly correct. So it's like if you use two identical thermometers, right? If you use two identical thermometers and if you measure the temperature, like if you measure the same temperature of the same, maybe same. So yes, let us assume this is identical, right? So if this is identical, means like these two thermometers are identical and it measures the same temperature of the substance. So what do you think? Will it show the same temperature? Actually no, right? So it may differ. The temperature shown by uh, the uh, the the thermometers might slightly differ. That is because they depend on they depend on how the temperature is absorbed, right? So there are a lot of factors that decides these absorption, right? So the absorption of heat, this temperature depends on the absorption of heat, right? So you can't 100% say that these thermometric substances are going to absorb the same amount of heat. It depends, right? It depends on the situation, right? So it depends. So therefore, like a small slight change is possible. A very small slight change is possible. So therefore, that is actually correct, right? So that is correct. Right. So let us see the next one, right? Uh, Actually, what they're saying in the next one is having a large contact angle between mercury and glass is an advantage for accurate uh, accurate reading in mercury glass thermometers. Yes, that is actually correct, right? Because if you see, like mercury is going to have a large contact angle, right? So if you see this, it's going to have a large contact angle. The surface tension, it's going to have a large contact angle. If it has a large contact angle, it's going to look like this in this case, right? So actually, what happens in that case is, uh, then what happens is this mercury column doesn't wet the doesn't wet the glass. It doesn't wet the glass, right? So when the mercury column has a larger contact angle, right? When it has a larger contact angle, it doesn't wet the glass, right? It doesn't wet the glass. In that case, it will show quick response, right? So therefore that is also correct. It is an actually advantage, right? It's an advantage because if it has a large contact angle, it will not wet the glass. If it doesn't wet the glass, it can quickly respond, right? It will quickly respond. Wetting the glass means if it wets the glass, what happens is it will take a lot of time to, like if it wets the glass, it will take a lot of time to uh, show some response, right? So it's not a good thing actually, right? So this is the best, right? So therefore that is also correct. So I guess you have analyzed, we have analyzed all the stuff that is required, right? So let us go for the fourth question in that case, right? So let's go for the fourth question. So yeah, so what they're saying here is, consider the following statements regarding the physical properties of ultraviolet waves and ultrasound waves. First of all, you need to understand the difference between the ultrasound waves and ultraviolet waves, right? So this is the fourth question, right? So actually, if you see ultrasound waves, right? Ultrasound waves and ultraviolet waves, right? So actually ultrasound waves is a sound wave, right? It's a sound wave, and ultraviolet wave is an electromagnetic wave, right? Electromagnetic wave, right? So sound wave means it is a mechanical wave. All right, sound wave means a mechanical wave, right? So that is the main difference between the ultraviolet and the ultrasound wave. So energy, so the A, let's consider the A statement. Energy of both waves depends on the frequencies, right? So let us see. So when you consider ultrasound waves, right? So let's consider ultraviolet waves, or else the electromagnetic waves. The energy of an electromagnetic wave can be written as E is equal to hf, right? We know that the electromagnetic wave, the energy is equal to hf, where h is the Planck constant. In that case, since this is h is a constant, we can say energy depends on the frequency. Energy depends on the frequency. That statement is correct, right? So is that the same for the ultrasound waves as well? So if you consider the ultrasound waves, right? So intensity is equal to E over AT, isn't it? The intensity of sound wave is equal to the energy of the sound wave over the cross-sectional area over the time taken. So energy is proportional to the intensity. Intensity is proportional to the square of the amplitude. Intensity is proportional to the square of the amplitude. I will use some other symbol, a squared, the square of the amplitude of the wave, right? So if you consider, it's proportional to the amplitude, square of the amplitude, intensity. So energy is not going to be proportional to the intensity. Energy, we can say, kind of proportional to the square of the amplitude, right? Energy is proportional to the square of the amplitude. It depends on the amplitude of the wave. It doesn't depend on the frequency of the wave, right? The energy of the sound wave doesn't depend on the frequency of the wave, right? So you need to understand that. So therefore that statement is incorrect, right? So therefore both, it's incorrect, right? Only ultraviolet waves depends on the frequency, the energy. Both waves have the ability of ionizing materials, right? So actually only the sound waves has the ability to ionize air molecules, right? Only the sound waves can ionize air molecules, right? So you know, but electromagnetic waves, they cannot ionize. They cannot ionize materials, right? So therefore, that is incorrect. All right, that is therefore incorrect. That message, that statement is also incorrect. Both waves can polarize, right? So what about the polarizability? So you know, sound waves, they cannot polarize, right? Cannot polarize, but ultraviolet wave is an electromagnetic wave. It is a transverse wave. Therefore, a transverse wave can polarize. Transverse waves can polarize, but longitudinal waves, right? Longitudinal wave, sound wave is a longitudinal waves. Longitudinal waves cannot polarize, right? But when you consider transverse waves, of course, they can polarize. Light is a transverse wave, it can polarize, but sound is a longitudinal wave, therefore it cannot polarize. Therefore that is wrong as well, which means all the three A, B, C are wrong, which means which of the following statements are incorrect? All A, B, C. All A, B, C. Right. So let us go for the next question as well. So in the next question, that is the fifth one, this is a question related with vectors, guys, right? So a basic question from the first unit, right? So they're saying an object is moving in a circular path, right? Okay, with a constant speed v, right? So with the constant speed v, as shown in the figure, the change in the velocity of the object when moving from A to B, the change in the velocity at these 2 points, right? So it's quite simple, right? So if you see, it's like this. So the fifth question, it's not very difficult, right? So it's like this. So that's the center here, right? This is the point B, right? This is the point B, and this is the point A, right? So actually this is the arc, right? So when the object is at A, what is its velocity? Let's assume VA. VA is equal to V. Always it's constant. When it is at B, let us assume the velocity is V B. What is its magnitude? It's V, right? We need to get the what exactly do we need to find? We need to find the change in the velocity. We need to find the change in the velocity. That means we need to find delta V. VB minus VA, change in velocity, VB minus VA, right? So you need to understand velocity is a vector quantity, right? So let us represent the two velocities, right? So let us represent the two velocities. Okay, VA, and this is VB, right? So the angle between these two velocity or the vectors, these two vectors are 90 degrees, right? So how would you get the difference between them, VB minus VA? By using this VA minus VB, or else something, right? So the modulus VA minus VB or VB minus VA. Let's assume VA minus VB. So this and this, right? This is what? This is going to be the difference between them, right? So let us assume VA or else VB. This is VB minus VA vector. This is a vector. How are you going to be given with this? The parallelogram law. The magnitude of this. How will you get the magnitude of this? Right? The parallelogram law. R is equal to VA squared VB squared. Instead of plus, we apply minus 2 VA VB cos 90. The angle between them is 90. So therefore the magnitude can be obtained by cos 90. Cos 90, this thing also completely goes to 0. Cos 90 means 0, right? So therefore the magnitude of the change in velocity between them. Vb minus Va can be obtained by the square. What is the magnitude of Va? That is V square. This is also V square, right? Sorry, this is squared, right? I forgot to mention square, right? So R squared is equal to 2V squared. So R is equal to V root 2. So this is the change in velocity, right? That is the change in velocity. Vb, so Vb minus Va, right? Change in velocity. Simply you need to use the parallelogram law. If you need to find the addition between them, that will be this this thing, what you call this gray diagonal, right? The primary diagonal, this is the secondary diagonal. So if you need to find the difference of two vectors, you need to use the secondary diagonal. If you need the addition of two vectors, you need to use the primary diagonal, right? So yeah, so the answer is for that is going to be what is it, right? Root 2v in this direction, 45 degrees, right? So this is 45. How do you say that is 45? If you assume this is theta, right? If you assume this is theta, and if you find the tan theta of this, tan theta is what? The opposite is v. The adjacent is also v. So the tan theta is 1. So therefore theta is equal to 45. Therefore this is 45 degrees, which means the answer is this. Okay, hope you understood that, right? So let us discuss the next problem as right. So let us go for the next problem, right? So it says a weightlifter lifts a weight vertically up. So the vertically upward direction is the positive direction. They have asked us to assume the upward direction as the positive direction with his hands, right? With his hands. So let us draw the diagram for this here itself, right? So let's assume this is the weight. This is the weight, and this is the hand, right? Right. So this is the, let us assume this is the hand, right? So let us mark the forces acting on this, the free body diagram. The weight is going to act downwards. The weight is going to act downwards, right? So the reaction, the action force acting on due to the weight, there's going to be an action force acting on the hand by the object, on the hand, reaction on the hand by the object. So like according to Newton's third law, therefore there's going to be another reaction, that is the reaction is acting on the object by the hand, right? So if you see the signs of these things, right? If you see the signs of these things, right? So this is W. This is like they have told us to take the upward as positive. They have asked us to take the upward direction as positive. So the force acting on the object by the hand is positive. The force acting, the work done, or the force acting on the hands, his work done by the hands on the weight, by the hands on the object, is positive. So therefore one of these three, gravity on the weight, gravitational force, gravitational work done is acting downwards, which means it is negative, right? Downward should be considered as negative. So either, now these two we have shortlisted to these two. Next, what? The weight on his hand respectively. So the work done by the weight on the hand, the weight done on the hand by the object, is downward. It is also negative. So the answer is the third one, right? Right. So let's go for the next problem, guys. The seventh one, right? So the seventh question, it's related with the lasers lesson, right? So it's related with the lasers lesson, and yeah, it's lasers lesson means like from the waves and oscillation, the final part, the laser segment, right? The laser section. So let us move on. So what it says is, consider the following statements regarding a 3-level laser, right? So here there's 3 energy levels, right? So usually we deal with only 2 level uh, systems, but in this case there's 3 levels for more stability, right? Having energies E1, E2, E3 as shown in the figure below, right? So we need to check whether these statements are correct, but before that I'll just give you guys a small heads up of a summary regarding the lasers concept, right? So this is the 7th problem. So yes, it's like this. So now let's assume there's 3 energy levels, right? So usually the photons are the electrons are in the ground state. Let us assume this is the ground state, right? So let's assume the energy of this energy level is E1, the energy of the second, this is E2. Let us assume the energy of this is E3 energy level, right? So what happens is, uh, if you what you need to do is, you need to incident you need to incident a photon, right? You need to incident a photon of energy E3 minus E2. You need to incident a photon of E3 minus E2. So what happens is, this electron will absorb the energy E3 minus E2 from this photon, and it will get excited, and it will reach to the E3 energy level. It will reach to the E3 energy level, right? It's not going to go to E2 energy level, right? It's going to go to the highest possible energy level to get excited, when it gets excited. So what happens is, okay, now by pumping, by pumping these kind of photons, right? Each one of these electrons at the ground state can be excited into the E3 energy level. So next what you need to do is, next you sorry, not here, right? Sorry. So next what happens is, this is not very stable. This position is not very stable. It's quite excited, right? So it's very excited, right? So this state is unstable, right? This is the excited state. So what happens is, right, uh, spontaneously this will jump into one energy level below it, right? It will spontaneously jump, right? So this is spontaneously, it will jump into E2 energy level, right? So this is an intermediate energy level. Intermediate energy level, we call this metastable energy level, right? We call this as metastable energy level because this is quite stable than E3. You know, right? So the when the energy levels has less energy, it's quite stable, right? So it jumps to this point. Now the electron is somewhere here, right? Electron is somewhere here. So next what you need to do is, you need to send you need to send you need to send uh, you need to send a photon with this energy. You need to send a photon simply, right? So let us assume to send a photon, HF, right? So what happens is, this electron gets induced. This electron gets induced, or this gets triggered. This gets triggered, and then what happens is, this jumps back to the ground state by releasing the energy E2 minus E1, right? By releasing this energy. This is the radiation. This is the laser radiation. This is the laser radiation, right? So first of all, you incident a photon, and by absorbing that energy, this electron will excite to the excited state. Next, it will once again come back to somewhat of an intermediate stable energy level. So next what you need to do is, you need to send a photon, right? You need to send a photon. So this electron gets triggered or induced due to this photon which grows closer to it, right? So as a result, this electron releases its energy E2 minus E1, and it jumps back to the ground state, right? So this energy, this photon will trigger another electron, and likewise this occurs as a chain, and you will get an electromagnetic radiation with very how do I say with uh, high intensity electromagnetic wave, that is laser, right? So that is going to be laser. So this is the basic summary, right? So like we did not consider in detail the basic summary. So the laser action occurs between 2 and 1. It's correct, right? The laser action occurs between 2, the energy level 2 and 1. So here only laser action occurs. Therefore, that is correct. The frequency of pumping radiation is E through minus E2 over H. So the frequency of the pumping radiation is this. This is the pumping radiation. E3, it is actually, we need to send HF, right? E3 minus E2 is HF. So the frequency is what in that case? E3 minus E2 over H. It's not, sorry, E3 minus E1. Sorry guys, right? So sorry, exactly, sorry, extremely sorry. So it's E3 minus E1, right? So from E3, E1. The energy level difference is E3 minus E1 over H. So E3 minus E2 over H. So this is incorrect, right? This is incorrect. Actually, it should have been E3 minus E1, right? Not E2. So level 3 is known as metastable. No, level 3 is not the case. Level 2 is known as the metastable state, right? The intermediate metastable state, level 2, not the level 3. So that is also incorrect. So the only correct answer is A. So the answer is going to be the first one. So actually, so let's move on to the 8th one, right? So this is going to be from the lesson waves, speed of sound in air, right? Speed of sound in air, right? So right, let us see the question. Consider the following statements made regarding the velocity of sound in Earth atmosphere. So the what is the equation? First of all, let us write the equation. V is equal to root gamma RT over capital M. There is another equation for velocity of sound in air, that is gamma P over rho, right? So these are the two equations for the velocity of sound in air, right? So they're saying it does not change. Okay, it does not change with altitude at constant temperature. So simply you need to understand what happens when the altitude of, okay, so from the sea level, right? So from the sea level, if the altitude increases, right, what happens? The altitude increases from the sea level, so what happens is the pressure will decrease, obviously you know that, and the temperature will also decrease, right? The pressure will decrease and the temperature will decrease. So you might say, okay, according to gamma P over rho, so pressure decreases, so therefore you might think velocity decreases. No, right? So you need to understand one fact very well, that the pressure or the density, the velocity doesn't depend on the pressure or the density, right? Velocity doesn't depend on pressure or the density, because whatever the change that you do to the pressure, it is going to change in the density as well, which means like if according to, like if you change the pressure, if you increase the pressure, volume of the air column decreases. So from m is equal to rho v, when volume decreases, the density increases because mass is constant. So when you increase the pressure, density increases as well. So this increase to this increase cancels, and actually no change, no resultant change. So therefore the velocity doesn't depend on pressure and density. So therefore when you keep the temperature constant, they are saying in the first A part, when the temperature is constant, uh, it does not change with altitude. Yes, actually when going up, pressure decreases, but does it matter to the velocity? No, it doesn't matter. Therefore, velocity doesn't change, does not change when going up, when the temperature is kept constant, right? So therefore that is actually correct. That statement is correct. It always increases with decreasing pressure. No, it doesn't depend on the pressure. The velocity of sound doesn't depend on the pressure. It's correct. It's incorrect, right? It doesn't depend on the pressure. It decreases with increasing altitude. So when the altitude increases, temperature decreases, so therefore the velocity decreases, right? So when the altitude increases, the temperature actually decreases. Due to the decrease of temperature, according to V is equal to gamma RT over capital M, right? When this decreases, velocity depends on the temperature, right? So it's a quite well-known factor. So therefore this is correct, which means A and C is correct. The fourth one is correct. So let us go for the next problem, that is the ninth one, right? So this is a question from thermal physics, right? So and also this is a question belonging to the gases part, the kinetic theory of gases part in the thermal physics, right? So it's quite an easy question. You just have to substitute the values to an equation and get the answer, right? So these kind of problems are given as bonus questions to get the marks, right? So if you are going to make mistakes in this kind of easy problems as well, so then there's no point, right? So you need to like for chemistry students and all, so these questions are going to be pretty easy, right? So anyways, let's move on. Hydrogen gas in a container is maintained at standard temperature. It's maintained at standard temperature 300 Kelvin and pressure this much. If the root mean square speed, it's not the mean square speed, it's the root mean square speed. What is the density? So we know actually we know that the ninth one, right? So if we consider this thing, right? So a gaseous container, the pressure is 1 into 10 to the power 5. Pressure is 1 into 10 to the power 5. Temperature is 300 Kelvin, right? And then the root mean square speed. The root mean square speed is 2 kilometers per second, right? 2000 meters per second. 2 kilometers per second means 2000 meters per second. All right. So fine. Let us move on. So we know the relationship between the pressure, temperature, the density. What they need is the density. That is C squared bar. We know that it is 3p over d. C squared bar is 3p over d. We know this equation. How did we get this? From the basic equation, PV is equal to 1/3 m n C squared bar. M into n is 1/3 mass of a gas molecule into number of gas molecule is m gas, right? Mass of the gas, C squared bar, divide the P is equal to 1/3 m gas divided by the volume of the gas. So mass of the gas divided by the volume is going to be what? The density, C squared bar. So if you subject C squared bar, it's going to be this, right? So better remember this equation, all right? So C squared bar, they have given the root of the mean square speed. So therefore, I'm going to take the root of both the side, or else I'm going to score. Yeah, what we could do is, instead of going with the root and all, we can do it in a separate way. C squared bar is what? 2000 squared, because the root mean square speed is 2000. So if we need the C squared bar only, we need to square both the sides, right? So square, right? So in that case, 3, what is the pressure? 1 into 10 to the power 5. Temperature doesn't matter. What we need is the density. Density is equal to 3 into 1 into 10 to the power 5. 1 into 10 to the power 5 over 2000 squared, over 2000 squared. right? So in that case, if you simplify, the density is going to be something closer to 0.075 kilograms per cubic meter, right? So therefore the answer is going to be 0.075 kilograms per cubic meter. That is the second answer, right? So let us go for the the 10th question, right? Let's go for the 10th one. It says this actually is a question from the lesson waves, right? So the lesson speed of waves in longitudinal, the speed of longitudinal waves in solids, right? So if you see, a composite rod is formed by connecting two rods A and B as shown in the figure. Longitudinal waves velocities in rods A and B are 3210, 6400 respectively. A longitudinal pulse is applied at the free end, at this end, right? A longitudinal wave pulse is applied. So at this A, the wavelength is 2. What is the wavelength on B? What's the wavelength on B, right? So yes, I guess this is a quite easy question, right? So this is actually the 10th one, right? So it's like this. There's a rod, right? So this is one type of rod and this is another type of rod, right? So actually when the when the at this, of course, VA, the speed is what? The speed is 3210. 3210. The speed of the longitudinal wave in the other medium is 6420. 6420. Now you need to, from V equals F lambda, when there was a medium change, so this is the medium 1, right? And this is the medium 2. When the medium changed, right? So when the wave was entering from this medium to this medium, right? So this is a longitudinal wave, right? So when it entered from medium 1 to medium 2, what changed was the velocity. Actually, the velocity has increased. When the velocity increases, what will happen to the frequency and the lambda? Actually, you need to understand very well. Due to a change in medium, the frequency will not change. When a wave enters from one medium to another medium, frequency does not change. Frequency does not change. Why is it? Because the frequency depends only on, it depends, right? It depends only on what? Only on the source of vibration. So it depends only on the source of vibration. So whatever the source which was used to vibrate here, the frequency is depending on that only. So therefore, when the velocity changes, what changes is the lambda. So we need to understand, in this case, the velocity is going to be proportional to the lambda, right? Velocity is going to be proportional to the lambda. So therefore, initially the speed was this much and the lambda at this was given to be as 2 meters. Lambda a was given to be as 2 meters, right? So when the velocity is 3210, the lambda is 2 second, and when the speed is 6420, we need to find the lambda b, right? What I'm going to do is I'm going to divide third equation from the second equation. 6420 3210 is equal to 2 lambda, sorry, lambda b over 2. This 2, this cancels, it's 2. 2 into 2 is lambda b is 4 meters. So therefore the answer is going to be 4 meters, right? So that's a easy question, right? So that's quite an easy question. So okay guys, let us discuss the 11th problem. So this is a circular motion problem, right? So yeah, let's see what it says. It says an air mass in a cyclone moves around its eye in a spiral path as shown in the figure. The velocity of the air mass at a radial distance of 80 kilometers, right? So the velocity of the air mass at a radial distance 80 kilometers from the center of the eye is 150, right? So from 80 kilometers, the velocity of the air particle at this point is 150. What could be the velocity of the same air particle at a radial distance of 40 kilometers, right? So what will be the velocity at this point? The same air particles velocity at this point. So that is quite a simple question if you see, right? That is because, like, if we consider the air particle is at this point, we can assume the inertia, moment of inertia at that point of the air particles moment of inertia at that point is I1. We can assume the angular velocity of the air particle as omega1 because it's performing a circular motion, and the velocity is mentioned to be as 150. So in the same way, we can assume when the air particle is somewhere here, we can assume its moment of inertia as I2, its angular velocity as omega2, its velocity as v2. This is what we need to find, right? So can't we apply the concept of what angular momentum at 80 kilometers is equal to angular momentum at 40 kilometers? We can, right? Because simply there's no external torque applied. Therefore, the angular momentum at 80 kilometers is equal to the angular momentum at 40 kilometers, right? So therefore, that we can say I1 omega 1 is equal to I2 omega 2. What is I1? Actually, the moment of inertia of a particle at a distance r from the center can be written as m r1 squared. What is omega 1? So actually, from v is equal to r omega equation, we can subject omega to be as v over r. So here we can write it as v1 over r1. This is once again the moment of inertia at a radial distance of r2 is m r2 squared, right? The velocity is v2 r2. So if we cancel these things, so this cancels, this to this cancels, mass to mass cancels. So the remaining is v1 r1 will be equal to v2 r2. v1 is 150, r1 is 80, v2 is what we need to find, r2 is 40. v2 we are going to get therefore as 300 kilometers per hour. We are going to get it to be as 300 kilometers per hour, right? So therefore that's done. Okay, let's get going with the next problem. Right, let's move on to the 12th question. This is going to be a question from thermal physics, right? Actually, this is a quite good question, right? So you need to analyze it very well. Okay, so it says an ideal gas expands from the state A to state C, right? So from state A to state C along two different paths are A, B, C, that is one path, and another path is A, D, C, as shown in the PV diagram. The heat absorbed by the gas during the process AB. During the process AB, heat absorbed is what? Heat absorbed is delta QAB. Heat absorbed is 200 joules, right? And in the process BC, the heat absorbed, right? Heat absorbed in BC. Heat absorbed means plus, right? So delta QBC, heat absorbed is plus 700 joules, all right, respectively. What is the change in internal energy when the expands along ADC? What we need to find is when the gas expands from A, D, and C, ADC, we need to find the change in internal energy. That means what we need to find is delta U AC, right? You need to understand that this delta U AC is path independent. That means this doesn't depend on the path. It doesn't matter whether you go from this path to this path, like from A to C using this path or this path. The internal energy is state dependent. That means like it depends only on the state. Okay, we like the initial state is A, the final state is C. So the internal energy change is UAC is UC minus UA. The energy at this point minus the energy at this point, right? So the energy change is this. So it doesn't matter whether you go from this path or this path, it's the same. It's not going to change. It's always UAC. Whether you go from this path or whether you go from this path, the internal energy change is always UAC. That is UC minus UA. It's path dependent, path independent. All right. So let us solve this problem. So to solve this problem, what I'm gonna do is I'm gonna initially I need to find the work done by the gas in the B to C process. I need to first of all find the work done by the gas from B to C process. In this process, how would I find it? By finding the area under this curve, right? How would I find the work done by the gas in B to C process? How would I find it? By finding the area under this curve, right? First of all, I need to find it. Why am I finding it? Okay, you will know it. You will know it, right? So, what is it? 6 into the area is 6 into 3. 6 into 3, right? So this is the 12th question. Is that the case? The 12th one, right? Yeah. The work done by the gas in the B to C process is 6 into 10 to the power 4. 6 into 10 to the power 4. 6 into 10 to the power 4 into length into breadth. This difference is 3 into 10 to the power minus 3. This is going to be 6 into 3 is what is it? 18, 180 joules, right? We have found that out. I have found that out. But I have found the work done by the gas from B to C in the B to C process. Now what I'm gonna do is I'm gonna apply the first thermodynamic equation, right? Equation for the first law of thermodynamics from A to C. I'm gonna apply the first law of thermodynamics from A to C, right? So from A to C, from A to C to the process A, B, C, first law of thermodynamics, right? First law of thermodynamics I'm going to apply. So what is the first law of thermodynamics? Delta Q is equal to delta W plus delta U, right? So this is it. So that is delta Q A C delta W A C delta U A to C. Actually A to C. In between there's another process. Therefore we can break this into heat absorbed A to B first and then B to C. First heat to A to B and then B to C. Work done from A to B and then from B to C. Do I need to break this? No, because for this is what they are asking. The internal energy change from A to C process. So therefore I will leave it as it is, right? So I'm not gonna break it. So delta Q AB, they have given it, I guess. They have given it delta Q AB 200 joules and delta Q BC is also given 700 joules, right? 200 joules and 700 joules. It's given. It's given 200 joules plus 700 joules. Delta WAB is what? What is the work done in the AB process? The work done in the AB process is 0. Why? Why is the work done in the AB process 0? Because work done is P delta V, right? So here the change in the volume is 0. No change in the volume. There's no change in the volume. Only the volume is always going to be constant. 3 throughout this process. Which means the change in volume is 0. Therefore the work done from A to B process is 0. What is the work done from B to C process then? It's the area under this curve. We found it, right? So this is 0. A to B is 0, right? This, of course, we found it. What is it? The work done from B to C process, we found it 180 joules. Now what we need to find is delta UAC. So 200, 700 is 900, 180, delta U AC. So delta U AC in that case is going to be 900 minus 100 is 800, 800 minus 80 is 720 joules. So the answer is going to be what? 720 joules, because it doesn't matter whether you go from this process or whether you go from this process. The change in the internal energy is always going to be the same. And so the answer, like without considering this path, I consider this path. Why? Because they have given the delta Q of AB and delta Q of BC is given. So therefore I had to use this path instead of using this path, because in this path they have not given the delta Q of this and this. So I had to go with this and find the internal energy change. Okay, let's move on, guys. So let's go and discuss the 13th one. Because this is a mechanics question, right? So not a very difficult question, I guess, right? So yeah, let's get started with. It says a ball is dropped freely to a floor from a height 1 meters, right? And if its speed is reduced by 25% at each bounce. So when a ball is falling and when it bounces, when it is rebouncing, its velocity decreases by 25%. What would be the height the ball reaches after the third bounce? Height. Okay, it's quite simple, right? So we will see a figure for this, right? Let us see a figure. Initially, this is the 13th question. Initially, the ball is released from a height, right? Height 1 meters. What happens? The ball is going to reach the ground. Let us assume with around, let us assume it's going to reach the ground with around v1 velocity. Let's assume it's going to reach the ground with around v1 velocity, right? So once it rebounces, what happens? When it rebounces, its velocity changes. Its velocity now is not v1, it's v2. It's v2. You need to understand this v2 is like from v1, or like they have told in one bounce, when it bounces, the velocity reduces by 25%. So what is the remaining velocity then? If it reduces by 25%, what is the remaining velocity? It is 75% out of v1. Now v2 is 75% out of v1, because like they are saying, when it bounces with the flow, when it collides with the flow, 25% is going to be lost. 25% of the velocity is going to be lost. What's the remaining velocity? 75%. Quite simple, right? Yeah. Okay. So what happens is next it's going to go to a maximum height, and then once again it's going to bounce, right? Once again it's going to bounce. It's going to come back also with the same velocity v2, but this is the first bounce, right? First bounce. Now therefore here the second bounce occurs. When the second bounce occurs, further its velocity decreases. Now it's not v2, it's v3. Now it's v3. How much is v3? V3 is also 75% of V2. 75% of V2. 75% of V2. Need to understand that. Because in this bounce also there's 25% going to be lost. Next what happens, it goes to a certain height and once again it returns back, right, with the same V3 velocity, right? And then once again it's going to rebounds. This is the third rebounds, right? This is the third bounce. At this point the velocity is going to change to V4. Now it's going to reach a maximum height. Let us assume H dash. We need to find this H dash, right, after the third bounce. So V4. So what is the V4 then now? V4 is also 75% out of V3, right? So actually to solve this question we need V4. We need V4. So I'm going to find V4. What V4 is? 75 out of 100 of V3. What is V3? V3 is this. V3 is once again 75% out of V2. What is V2? V2 is 75% V1. 75% V1. V1. Right? So simply V4 is 75% V3. Instead of V3, I substituted this expression here. So instead of V2, I substituted this expression here. So I got this, right? So what is V1 now? You need to find V1. V1 is quite simple, right? So V1, conservation of energy. Energy initial state. That is mgh. Initially it fell from a height mgh. When it reached the ground, it had a velocity v1. So let us write half m v1 squared. M to m cancels. So v1 is root 2g h. What's the height? Height is 2g. Height is 1 meters. So v1 is root 2g, right? Root 2g. Therefore v4 is what now? V4 is 75 over 100 cube V1. V1 is root 2g, right? This is 75, 3 over 4. We simplify this to this, 3 over 4 cube root 2g. Now we know V4. Now we know the V4 height. We know the V4 height. So this is the initial kinetic energy. Until this kinetic energy is going to become 0, it's going to reach at it's going to reach a maximum height. At this point velocity is 0. Therefore the complete kinetic energy converts into potential energy, right? The complete kinetic energy converts into potential energy. So after the third bounce, right, after third bounce, I'm gonna apply conservation of energy once again. In that case, half m initial kinetic energy was what? V4 squared mg. It reaches a maximum height of h dash, mg h dash. So m to m cancels. V4 squared is equal to 2g h1 dash. So what's V4 squared? This squared, 3 over 4 cube root 2g. We need to square it, 2g h dash. Okay? So if you square it, it's going to be 3 over 4. 3 into 2 is 6, 2g. This root goes off, 2g h dash. This 2g to 2g cancels out. H dash is 3 over 4, 6, 3 over 4 to the power 6 meters. 3 over 4 to the power 6 meters, which means the answer is this. Hope you understood. Right. So if you see the 14th one, right? So this is Newton's laws problem, Newton's laws of motion problem, right? So let's first of all read the problem. Hence, consider a massless balloon attached to one end of a light string. The other end of the string is attached to a bottom of water tank which is fixed uh, in a truck as shown in the figure. The balloon is completely submerged in water. The velocity time graph as shown the below. This is the velocity time graph of the truck, right? So what we need to understand is, so initially it's moving with an acceleration 0, gradient 0 means acceleration 0, gradient negative means acceleration, it's a deceleration, right? So this is what happens, all right? So first of all, before we discuss this, I'll give you a small overview of this kind of a problem, right? So if you consider this kind of a figure, right, and this has the object. Now the surrounding to this object is with higher density. The surrounding to this object is with higher density. According to the inertia principle and all, we have discussed, uh, we have actually, uh, we already know this stuff, right? So like that is because based on the inertia concept, we know that when the surrounding density is high, right? So when the surrounding density is high, high, then when the object moves, when the system moves forward with an acceleration, this is with a lesser density when compared with the surrounding, right? This is less density, sorry, this is less density, less denser than the surrounding. Therefore, in that case, this will move forward. This will move forward. It's going to look like this, right? So the surrounding in that case is going to move backwards, right? It would have been nice if the if the liquid column was given as this, right? Only up to this much. In that case, the surrounding is going to look like this. The surrounding is going to go back, and the surrounding is going to go back, right? And the uh, object with the lesser density moves forward because it has lesser inertia, which means it can quickly change its motion and it can move forward. But the surrounding has a higher inertia, higher density, higher inertia, which means it has a higher reluctance to change its state of motion. It will slowly change its state of motion. In that case, it will bend towards the backwards, right? So, but here, since it's completely filled, we do not have to consider the motion of the this thing, what you call the figure, the motion of the uh, surrounding, right? What we need to consider is only the motion of the uh, balloon. Actually, the balloon is less denser than the surrounding, therefore it has a less inertia, therefore it quickly changes its state of motion. If the if the vehicle is moving forward, it quickly moves forward. It quickly moves forward. So initially, when the acceleration is in the forward direction, when the acceleration is in the forward direction, the balloon quickly moves towards the front. Ah, right. Either this or this, right? Ah, right. Next, when the acceleration is zero, there's no motion. It will be as it is, right? There's no motion. It will be as it is, right? Uh, this, yeah, this, right? When the acceleration is in the backward direction, it means deceleration, right? The negative acceleration means deceleration. It's like the acceleration is acting in this direction, which means it will be in this, right? So the answer is fourth one. So actually, guys, you can decide about this in many various ways as well, right? There's many other steps, like you can consider the pressure from this side, right? Like pressure towards the right is greater than the left when the object is moving forward, therefore it's going to bend towards the forward. Like likewise, there's plenty of theories, but I prefer to go from the inertia concept, and I have taught our students as well to shortlist a method, actually, that is, if the object's density is less than the surrounding, then it has lesser inertia, then it will quickly respond towards the direction of motion. So surrounding will respond slowly. That's how we have made out some conclusions. So I think this is easier than the pressure concepts and all. So the answer is fourth one, right? So yes. So let us go for the 15th question. So in the 15th question, what it says is, the saying, consider 4 metal balls of the same volume placed on a smooth horizontal surface. Mass of each of the first balls is simple m. So mass of the first 3 balls are simple m, while the mass of the second ball is 2m, right? So mass of the first ball is m, fourth ball is 2m. They are equally separated in a straight line. The first ball moves with a velocity v, right? So initially the first ball moves with a velocity v and collides with the second ball, resulting a series of linear elastic collisions, right? This is very important, linear elastic collisions, right? After all the collisions, the motion of each ball is best represented by. So what you need to understand is, right, here if you see, they have told that the each and every collision is what? Elastic, which means what? Which means the energy of the system is conserved, right? Conserved. The energy of the system is right? The system is conserved. The energy of the system is conserved. Initially, so what they're saying is, like, after the collisions, the motion of each pole is going to be represented by. You need to see which of the following system correctly represents the motion after all these collides with each other. So it's like this initially, right? This is the 15th one, right? Initially, all the objects are at rest. This guy is moving with velocity v, right? These guys are at rest, 2m, right? So what is the initial linear momentum of the system? Initial linear momentum of the system is mv. In which direction? In this direction. What is the initial energy? Initial total energy of the system? What is the initial total energy of the system? Half m v squared. These each and every object is going to be at rest, right? So we know, since there's no external force applied on the system, since there's no external force applied on the system and no energy loss, I mean, like, since the collisions are also elastic, the system is, we can apply conservation of linear momentum and conservation of energy to the system, right? To this system we can apply conservation of linear momentum and conservation of energy. So somehow, if we apply conservation of linear momentum, what should happen? The initial linear momentum should be equal to the final linear momentum of the system. It should be equal to the final linear momentum of the system. So what is the initial linear momentum? mv in this direction, which means the final linear momentum. Somehow, after all the objects collides with each other, finally the linear momentum of the system should also be mv in this direction. What is meant by the conservation of energy? Conservation of energy means the initial total energy should be equal to the final total energy. What is the initial total energy? Half m v squared, which means the final total energy of the system after each and every objects collides with each other should also be half mv squared, right? Half mv squared. This is very important, this equation and this. So finally, the linear momentum of the system after each objects collide should be mv in this direction, and the final total energy should be half mv squared. Energy is a vector scalar, so therefore there's no direction for the right. So remember, right? So it should be mv in this direction, final linear momentum. The final total energy of the system should also be this, right? So let us, like, we will, in this kind of a problem, we will have to use a elimination process, right? So just see this first one. mv in what is the final linear momentum of the system? mv in this direction. So will it be valid? No, because we need mv in the other direction, but in this case mv is in this direction, so therefore it's wrong. Let's go for 2. If we go for 2, what is the final linear momentum? 2mv over okay, right, it has mv in this direction. So is this the answer? No, we need to check the, so okay, the conservation of linear momentum matches. The final linear momentum of the system is equal to the initial linear momentum, but we need to check the final energy of the system. So final energy of the system is this 0, this 0, this 0. We need to check the final energy of half into 2m into v over 2 squared. This to this cancels. mv squared over 2, not 2, 4. But the final linear momentum is what? This, it should be half mv squared, not 1 over 4 mv squared. So this is also wrong. So we need to check this as well, right? You need to check this as well. This is going to have a linear momentum 2m into 3v over 4 minus, this is in the other direction, right? If we consider the linear momentum, this is in the other direction, m into v over 2. So this to this cancels 2, 3v over 2 minus mv over 2. This is mv. Okay, it's fine. It is having a linear momentum in this direction. Shall we check the total kinetic energy? Total kinetic energy, if we check, half m v over 2 squared. V over 2 squared is v squared over 4. And then this plus 2m over 2, half 2m, mass is 2m, 3v over 4, which means squared. If we add this, you will not get half mv squared. Half mv squared, you will not get that. Now this is also wrong. But if you apply conservation of linear momentum to this system, you will get it's mv in this direction. And when you apply unify the total kinetic energy of the system, you will get half mv squared. You can apply this and see. So therefore this is the answer. The fourth one is the answer. So actually guys, you will have to use a elimination process to solve this, right? So if you go to apply equations and try to find the final system, it's going to be quite lengthy. So therefore better use an elimination process as this, right? You check the mv, check the linear momentum of this one, this one, this one, this one, this one. So and then thereafter you have to check the energy of the system. So you need to check whether they are equal to these values, this and this. So only the fourth answer gives this as this. So that will be the answer, right? So here what it says is, this is actually a Bernoulli question, right? So it's a Bernoulli question. So in this, of course, what it says is, as shown in the figure, an incompressible liquid flows steadily through a horizontal pipe, right? So what flows through is an incompressible steady flow, right? So and then they're saying two narrow vertical tubes are fixed at two places horizontal pipe. So that's two narrow tubes fixed, right? So this actually is used to measure the pressure, right? So by using this narrow tube, we can measure the pressure. So the areas of the pipes are A and 2A. The height difference of the liquid column in these pipes are of height h. Then they are asking find the flow rate of the liquid through the pipe. They are asking the flow rate of the liquid through the pipe. So in this case, of course, let us initially draw a simple diagram, right? And then thereafter we will discuss further the